webcast is now starting. All attendees are in listen-only mode.
Welcome everyone to today's webinar, Getting Specific About Coating Specifications, presented by North American Coating Laboratories and hosted by Photonics Media. My name is Robin Riley and I am the Photonics Media web editor. I would like to introduce today's speaker, Mr. Dan Fiore, Director of Business Development at North American Coating Laboratories. Dan has more than 14 years of experience in the optics field and acts as a single point of contact for all of NACL's industrial optical customers. He'll be answering your questions and speaking today on how to specify, test, and confirm that your coating needs are clearly stated and conveyed to your coating solutions provider. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. We encourage you to ask questions throughout Dan's presentation. Please type your question in the question box to the right of your screen. And with nothing further, I would like to turn the presentation over to our speaker today, Mr. Dan Fiore. Good afternoon, Dan.
Hi, Robin. Thanks so much. And thanks everybody for registering. Definitely appreciate that. Welcome. And, this will be our presentation, Getting Specific About Coating Specifics. I want to take the time to thank Robin for hosting and for Photonics Media for putting on the webinar. Robin actually informed me that this is her first webinar since the start of the COVID-19 outbreak. And it really is. It's truly challenging times that we're all facing in all business sectors. We've all had to adjust to remote work environments, and collaboration is increasingly more challenging. This webinar was scheduled in advance of the COVID-19 outbreak, but now more than ever, it seems pertinent to us here in the photonics industry. Now, because of our unique challenges we're facing, we'll need to be more collaborative and more communicative when it comes to all the specifications we decide to use when creating some of the cutting-edge optics we're all involved with on a daily basis. NACL's goal as an organization was to present a nice 50,000-foot view of the specifications that we see multiple times per day and how to use those specifications. We also wanted to shed some light on the subjectivity of optical coating specifications. Many of these can be amended without any sacrifice to the integrity and to the application the optic is intended for. So without further ado, definitely want to get started here. Just kind of a brief heads up. The presentation and slide deck itself is slated to go about 45 minutes. At that time, I'll turn the controls back over to Robin for a Q&A session. So I will begin. Okay. So really, when putting this all together, we wanted to kind of point out, like I said in the intro, a 50,000-foot view of what are the critical specifications, what are the critical tolerances for all of the different coating types. We see multiple drawings a day and have to come up with multiple quotes a day and see all different forms of specification: reflectance, transmission, operating wavelength, angle of incidence. There's mechanical requirements all the way down to sheet resistance or electrical requirements. So really, again, this is going to be a 50,000-foot view of what we see every day, how we negotiate that, what we're more likely to take exception to, what is a pretty straightforward specification, and then some of the off-the-wall things that we do see from time to time, depending on the application and depending on the business sector that the quote is coming from. So really kind of the meat and potatoes, the real start of any optical coating specification is going to be the reflectance and the transmission of the optical coating specification. So this is almost always measured with a spectrophotometer. All coating runs include a witness coupon, and this is an index matching material. For the measurement of light transmission, the witness chip is clear, so you can measure the transmission of light through it. If transmission is a critical aspect of your specification, the witness chip will be coated on both sides. If reflectance is the critical aspect that you're measuring, the witness chip will actually be frosted and blacked on one side. That way we can get a true single surface measurement off of the witness coupon. If we weren't so to frost or blacken the backside of the witness chip, you would have to incorporate about 4% surface reflection from the back side. So usually there'll be multiple witness chips run at multiple positions in the chamber, and they'll all be measured. The spectral requirements, when they're written on a drawing, are typically specified as an average requirement or an absolute requirement. Now, overall, that doesn't seem like a huge difference, but it definitely is. Average requirements basically state that over the specified wavelength range, the permitted amount of reflection or the permitted amount of transmission, expected permitted, will meet an average number that's agreed upon. Now, an absolute specification, just as it sounds, mean at every point throughout the operating band, the absolute requirement must be met. Doesn't seem like a huge difference, but it is. If you're taking a standard visible anti-reflective coating from 450 to 650 nanometers, and you're measuring the reflectance of it, if at 451 nanometers we're at 0.51% reflectance, then by letter of the law, we have to reject this coating lot. And that is really the difference of just a simple word, just simple wording, and maybe not even the intent of the specification. So as I get down further into the slide deck here, we'll talk a little bit more about the subjectivity of specifications and when we would take exception and when we may steer the coding specification to probably what is more intended by the designer as opposed to following the letter of the law of the specification if it maybe drives away from being effective, producing a good yield, and being a realistic, achievable, manufacturable specification. So I used a few words there kind of talking about reflectance, transmission. These are all probably review for most people involved, but operating wavelength is basically measured with a spectrophotometer, and it's really asking, where is my sensor operating? How is it interacting with light? If I'm working on a visible spectrum application, 400 to 700, what have you, take 50 nanometers left, 50 nanometers right. If I have a near IR requirement, I don't really need to specify too much in the visible if my sensor's telling me I don't need to. So understanding how your sensor or how your application is interacting with which specific visible spectrum is extremely important. That helps us decide on what materials we're going to use, what thicknesses we're going to need to deposit. A vast array of other aspects go into deciding what coating we're going to use to meet your specification. Operating wavelength is probably the key in almost all of those. Another requirement is angle of incidence. Angle of incidence is basically how is the user or how is the sensor going to interact with the light off the surface. This is also measured with a spectrophotometer. There are some automated and more mechanical ways that this can be measured. An automated way to measure this would be using a automatic reflectance or automated reflectance accessory. The other way would be an integrating sphere, which is more of a mechanical sort of solution. And really finding out how you're going to interact with light is vital to specifying angle of incidence. Adhesion is really important. That really is what makes a coating a coating. So with adhesion, you have to ask yourself, is your coating going to stick? And how am I going to test how it's going to stick? Abrasion resistance, and then also the sequence you're going to be testing in. These are all very important requirements. Flexibility with the specification, again, we're getting into that subjectivity. Is pass-fail really pass-fail? So with adhesion requirements, this is almost always a cellulose tape test. Cellulose tape test, it's your Scotch 3M tape. MIL C675 came out in the late 60s, early 70s. It's a very rudimentary specification. You're basically putting cellulose tape down on your coated surface, you're rubbing, and you're pulling it away. Now you get into the subjectivity of the specification. Am I pulling this away quickly? Am I pulling this away slowly? At what angle am I pulling this away at? And how tightly do I have to put the tape down on the surface? That's really some of the subjectivity of the specifications and how you maneuver through them. So the way that we understand this is you go towards the middle of the substrate, you tightly adhere the cellophane tape, and you pull away aggressively. That is really how you should test adhesion. But again, depending on how you're testing or your customer requirement, it could be a little different. You'll see in MIL M 13508, paragraph 3.9, because this is a mirror coating, which are typically softer than other dielectric applied coatings, the pull away is a little slower. It can, and then you have the subjectivity of how fast is a fast pull, how slow is a slow pull. So again, you can get lost in the weeds really quickly when you talk about something like adhesion, but there are some definite parameters that you can discuss with your coating professional and kind of let them know where you stand, what type of application is going to be used, how much the part is going to be handled. So adhesion is always extremely important. It should always be tested, but again, there's some subjectivity with how you're testing and different things of that nature. So the Scotch brand 600 M tape is what you'd use. Again, there's a specific MIL spec, MIL MLT 90D AA 113B, that basically specifies the exact type of tape to use. In some cases, you'll also see customer specified adhesives being used. We have an application that we know our customer will actually be adhering to a part with some special technical tape. They'll be doing some after assembly and actually putting this in a boot that goes on an airplane. Obviously, the adhesives they're going to use in an avionic application are going to be far more aggressive than a Scotch tape. So with them, with collaboration, we actually came up with a certain type of tape that we use, and we tape test all samples. So again, this is more of the collaboration and the subjectivity, really understanding what the form, the fit, and the function of your application is, and testing it in a real world scenario. The other thing you have to keep in mind here, and this is more on the protection and shipping side of things, are pressure sensitive adhesives or pressure sensitive films. A lot of times in shipping, customers, coating vendors, they're going to want to protect that film. You spend hours putting down a perfectly adhering film, everything goes great. Then you put a pressure sensitive adhesive over it, wrap it, send it away. So when you send it away, you have to imagine that the wrapped optic with the pressure sensitive adhesive goes through multiple environments. When it's going through these multiple environments, temperature changes, humidity changes, all different sorts of things happen, and there could be some interaction of the chemistry with the pressure sensitive film and the last layer of your coating film. So when specifying that there should be some protection on the surface and when specifying a pressure sensitive adhesive to be used, chemistry really has to be considered. And that's just kind of a pitfall that through experience we know, and understanding how to use pressure sensitive films, that also can help as you specify how to package, how to ship your optics. Now, it being an adhesion requirement doesn't really fall in, this isn't really testing, but again, it could show adhesion issues if you have a pressure sensitive film that removes your coating. So again, just kind of a pitfall and an issue that we've run into in the past. Another portion of adhesion requirements, and this is used more on highly durable coatings like diamond-like carbon or dip-applied polysiloxane films for polymeric optics. This is a crosshatch adhesion test. Just as it sounds, the tester would take a razor blade and score the coated optic. Coated optic is scored, then you place your tape, your 3M tape, over the scored optic and pull away aggressively. And as you can see here on the slide, we basically have a whole spectrum of failure. And then depending on where your customer specifies, you could see through this failure mode, what is acceptable. Can I take up to a 3B, 5 to 15% loss? Is that okay? You can also say, after 1 pull, I want 0% loss. After 20 pulls, I want 3B. After 100 pulls, I would expect 1B. So again, this is kind of collaborating with your coating supplier and understanding what the film is capable of. Adhesion loss, some more subjectivity. Where is the adhesion loss occurring? This is an important question to ask. If you could see some of these samples I have, this is right along the edge of the part. This is extremely common. What you have to ask yourself is, where on the optic is this occurring? And is it continuing to fail? If I can get the part to fail only on the edges, and through continually tape testing it, I can't get that failure mode to continue into the critical zone, then if it's outside of the clear aperture, technically I do have an adhesion loss, but I don't know that I have a failed optic. And again, we're into the subjectivity. The other place that if you measure tape adhesion is right at a tooling mark, right at the interface of your tooling versus your coated optic is going to be the weakest point of your coating. If you can imagine, the conformal film goes over the metal and then right to the optic, and there's a break in the 2 layers when you remove the optic from the tool. If you then go and test this weak point, you could find some failure in this area. Now, the real test is if you continually test and the film doesn't continue to fail and run into the critical zone, then technically you should have a passing optic. So there are environmental requirements too. And again, these are kind of the 50,000-foot view, the most common ones, but based on the form, fit, and function and how you're using your optic, these can all be changed. There are definitely some creative ones that I'll show you, and really just kind of how the optic is going to be used is really important. If you're talking about a mirror that's going to be used in a lab environment, then specifying 95% relative humidity at 80 degrees Fahrenheit, probably not super important for you. Again, thermal cycling going to be important, but again, having to consider the environment the optic is going to be used in is also important. So humidity standards. One of the most common ones we see is MIL C 48497. And basically it's at 120 degrees F, 95 to 100% relative humidity. So basically after this exposure, you're not going to see any signs of degradation of the film. You're not going to see any crazing or spider webs. If you test adhesion, you should be fine. And you're not going to see any haze in the film, like the surface of the coating was breached and there's moisture underneath. Another standard, and this one actually gets progressively more aggressive, is MIL 810E, method 507.3. There are 3 different procedures: natural, induced, and aggravated. Most coatings fall into procedure 1, sometimes procedure 2. With IR optics or optics used in extremely challenging environments, you'd probably want to opt for procedure 3. The cycling, again, 86 Fahrenheit to 140 Fahrenheit, and relative humidity, 95 to 85%. The duration on this is usually 10 days in the aggravated exposure mode. Thermal cycling, another important aspect that we have to explore. Thermal cycling is basically, just as it sounds, you're heating up your optic as you use it. you're getting it to a very high rate of temperature, and you're taking it down sub-zero. What you're supposed to model in the film is how is the film going to interact with the heat changes, and are we going to induce stress, create adhesion loss, or ruin the optical performance of the film? Again, there are different modes that we're going to explore here. Some are a lot more aggressive than others. One of the most common ones we see is MIL-C 48497. It's a real standardized test, and basically it's 2 hours at the high end and the low end with a 2 to 4 degree step down. You'll see this a lot on polymeric optics that can handle high heat. You'll also see it on cemented or bonded optics. It's not that it's not an aggressive test, it's just more real world. Super high temperature tests for optics that are going to be used in the desert, in assault vehicles, gun mounts, that sort of thing. Those would probably fall more into the MIL STD 810E, and you can read that specification there. Obviously, 7 24-hour heat cycles, 168-hour test overall. That is an extremely aggressive test, but if your optic is going to be used in an aggressive environment, you probably want to consider using that. Another aggressive test that comes into play, obviously, with military optics, optics used at sea, optics used in avionic applications, is salt and sulfur dioxide spray. So basically, you have a chamber and you have salt, sulfur dioxide in a mixture, and it's introduced into the environment, and essentially your coated optics sit there. There are 1-day tests, 7-day tests, and 21-day tests. Obviously, with the longer the duration, the more aggressive the test is. So this is actually data from some metallized pieces on just float glass. So you could see the effect that salt and sulfur dioxide spray have on coated optics. Again, this is a very important test to run on avionic applications, marine applications, and any outboard optic that'll be used in a challenging environment. So, abrasion resistance. There are 3 very well cited abrasion resistance requirements. MIL-C 675, MIL-C 48497, and MIL-M 13508. Almost all coatings are going to fall into the moderate abrasion mode, and that is essentially you have 25 cycles or 50 strokes of a cheesecloth, just a clean, dry cheesecloth that you'll run across the coated surface. You measure basically, how does it look before I do it? How does it look after? You can measure it with a spectrophotometer if you want to see if there's any loss in transmission, but more than anything, it's a visual check. If I stroke this coated side 50 times with this cheesecloth, am I going to induce stress on the film? Is the film going to be cloudy? Am I going to start to break the film up? Am I going to start showing scratches in the mirror where if I keep abrading, I can pull mirror piece up or pull the film away from the coated substrate? So again, this is a moderate abrasion test, almost always used in polymeric optics and a little less challenging environment optics. Anything used in a laboratory, anything used in a controlled environment that isn't going to be handled a lot or cleaned regularly is probably fine under moderate abrasion. Severe abrasion, very similar test with the strokes, but you actually have a calibrated pencil or pen-like device where you have 2.5 pounds of pressure and a rubber pumice eraser, and you pass this over the coated surface multiple times, and then again you perform a visual check for any induced stress on your film. Some severe abrasion and even some moderate abrasion testing, if the matrix of tests requires it, you'll do a severe abrasion and then do an adhesion test. You can do a humidity test, then severe abrasion, and then an adhesion test. So it really depends on how you want to stack the testing matrix and how you want to specify the tests are conducted. So those are a couple of abrasion requirements that exist, severe and moderate abrasion for those mil specs. This is kind of another off-the-wall specification that we received from a consumer electronics supplier. Basically, they're making smartphones. And the way everybody cleans their smartphone is take the screen and rub it on your jeans. So cheesecloth really didn't make sense, and a rubber pumice eraser was far too aggressive for what they wanted to do. How could they make basically jeans, a gene test, be a good abrasion test for their optic? So with their optical screen, what they did is they actually put it down in this test chamber, and they have basically a rotating head here, and it goes back and forth 250 cycles or 500 strokes with just 100% cotton denim. And again, it's a visual check. Okay, I've swiped that 500 times. I'm going to take a look at this surface and see, did I alter the transmission? Is the coating cloudy? Am I creating stress in the coating? Do I lose adhesion? Different things of that nature. Are there clusters of scratches? Anything like that. So you're really looking for a weakness point in the coating. Okay. So again, with infrared optics and optics used in extremely harsh environments, one of the things you'll have to consider too is if you use a coating such as diamond-like carbon, if there is kind of an alternative specification. One of the alternative specifications that we see for diamond-like carbon-coated IR optics is a windscreen stand slurry test. And basically, just like it sounds, this is going to show you virtually how your optic will react in a sandstorm, in a sand and rain storm, in driving wind storms, that sort of thing. So really, you don't want to see any visible damage, no abrasion, no coating removal, and none of the coating actually coming away from the surface of 10,000 cycles of a sand slurry or 5 minutes of abrasion at 1,000 RPMs. So these test setups are just like they sound. It's basically this slurry comes down over the coated optic, and you have a windshield wiper that's agreed upon and is specified, and it swipes right over the optic, and the damage to the coating visibly seen prior to and after the test is what's measured. Chemical resistance becomes important as well. So a lot of times, different cleansers are used on optics. No matter how many times we specify to use watered down isopropyl isopropyl alcohol and a clean microfiber cloth, that's rarely ever done. So what fluids, what surfactants, what cleaners can we use to really manipulate the optic and prove how it will perform in a real world environment? So MIL 810G is going to show some different ways. It's test method 504.1, where you're basically taking the chemical and you're applying it to the optic just as it would be in the real world. If it's completely immersed, then you're going to immerse it. If it's with a spray, you make sure it's sprayed over the entire surface. You don't shake it, you don't wipe it dry, and you leave it for an hour. After that, you slowly dry it and you check the surface for any visible damage. Some of the common chemicals that are specified here are insect repellent. We have an avionic application where between flights, bug spray is basically put, different pesticides are definitely put into the cabin of the plane to make sure any surface that's touched is cleaned off. But now it's more important than ever. But that insecticide definitely eats polycarbonate. So needed to check the efficiency of our hard coating, and one of the tests that was utilized was an insect repellent test. This comes into play with the machining industry and with the military for penetrating and buffing oil on gun components and things like that. If any of that oil is going to hit the optic, we need to test the optic and make sure that the minute that penetrating or buffing oil hits the optic, it's not going to eat the coating. Antifreeze, another one, different lubricating oils, vacuum pump oils, household cleaners. I have the generic glass cleaner there. That's a real important one because laymen or consumers in the field don't understand how delicate coatings can be. So then, hey, it's glass. I'm going to spray Windex on it and rub it with a paper towel. So that has to be a test that we simulate the actual real world use. And then outdoor applications or automotive applications, you're definitely going to want to test and specify resistance to suntan lotion and sunscreen. We worked with a theme park that had polycarbonate smart band readers, and our customer noticed, hey, we injection molded these smart band readers. We put them in the park, and 2 weeks later, all of them are hazy and the polycarbonate's starting to break down. Like, what's happening? Well, in a study, our customer noticed that kids, parents, all the people who were going to theme parks had sunscreen on their hands or suntan lotion on their hands, wanted to go up to this smart band reader and rub it, touch the surface because it had some cool LED lights. Well, all of that interaction with sunscreen and suntan oil on the polymeric optic created breakdown. So we were asked to hard coat this, and again, our hard coating had to stand up to a suntan lotion sunscreen test. Here's another kind of off-the-wall test. With smartphones, we have our lovely lady here exhibiting using a smartphone. People have different facial oil makeup. The oils from your face, if they get on a coated surface, they can definitely start to eat a film. So how can we simulate the oils in someone's skin? What was decided on was essentially olive oil water mixture, submerge the coated optic, remove the coated optic after a set period of time, say 10 minutes, look for any coating removal. Again, you're looking for any adhesion loss, any hazing, any crazing, any induced stress. The other tests that consumer electronics are big on are hair and cosmetics. Again, this is going to be just like a salt sulfur dioxide spray in a chamber. You're going to mount your optics, it's a sealed chamber. You introduce gas with hairspray and cosmetic chemistries. And then after a set period of time, you'll pull that out of the chamber and you'll inspect it for transmission loss, adhesion loss, or anything like that that may have interacted with the coating chemistries and created weaknesses. So away from some of the abrasion, adhesion, mechanical, and chemical interactions, this is clear aperture. Clear aperture is important because this tells us where the critical zones on the coating are, and then that actually tells your coating supplier, your coating partner, how to hold the optic while they're coating. A unique thing we're tasked with as a coating supplier is we need to hold a very, technically a very expensive optic that you've injection molded, you've diamond turned, you've fabricated, you've spent a lot of man hours, it's expensive material. It's going in our chamber, it's going to be warm, and it's going to be spinning around in deep vacuum. But we're tasked with not being able to hold the part very much or as lightly as we can. So when our customers specify to us the clear aperture of the part, what they're basically telling us is where can we hold it and what surface absolutely positively cannot be interrupted with a tooling mark. Here I have a simple kind of biconvex lens with a nice bezel all around the outside, or bezel all around the outside. So you could see the orange area is where I'll be coating. The dashed line is the clear aperture, and it's understood that anywhere outside of the clear aperture is acceptable for me to hold on to. So that's how we're going to talk about clear aperture and holder allowance. It's called tooling mark allowance. Those are some of the different ways it's specified. Outside of the clear aperture, we consider this as a non-critical zone. So anything outside of here is a non-critical zone. And to us, this means, okay, I can have a clamp mark. I can have the head of my tool that's going to hold the part on the part, and it will be suitable. It will be acceptable if there is a marking there where film may have interacted with the optic and my fixture. The other thing about clear aperture too, and again, we're getting back to subjectivity here, clear aperture, if a adhesion loss or if a coating flaw is outside of the clear aperture, is that still acceptable? We believe it to be. If it's outside of the clear aperture, which has been specified as the critical zone, then technically it should not count as a failure if you have poor adhesion and the coating film, the adhesion loss doesn't run into the critical zone, and the coating flaw, be it a pinhole or something else, is not in the critical zone. So outside of the clear aperture, really any flaw should be acceptable and any holder mark should be acceptable. But again, this would be subjectivity, and this would be something that you would need to discuss with a coating supplier so you're all on the same page as you move forward with the program. Okay, and this is just kind of an idea of some of the different holder marks. So what you have here in gray is an actual coating fixture. You know, sometimes it's called a pocket fixture or a drop-in fixture. And really what you have is a recessed area with a shelf, and the part will actually drop into the shelf, and the coating will go over the exposed area. And obviously where the shelf is over the optic, that part will be shielded from the coating. And what you'll have is kind of a clean concentric circle all around the outside of the part. So that's typically what on a circular optic, on an easy circular optic, your holder mark will look like. Obviously, if you're talking about a window, a square optic, a rectangular optic, you're going to have some sort of clamp, and your interaction with the coated surface is going to be a little different than a perfect concentric circle. Now, you can make frames in that sort of aspect where the entire outside portion won't be coated, but typically that'll add lead time and that'll add cost because of tooling custom frames for every sized window that you might specify. All right. So there is a more technical specification, and this does not fall in for a lot of optics, but it's laser-induced damage threshold testing. One of the most common specifications we see is ISO DIS 1125 and 21254. So essentially, laser damage is you're going to take a low power energy beam and you're going to direct it at the optic. The beam is going to pulse on the optic at 10 different locations for 30 seconds. And that will be for a continuous wave laser. So the number of pulses and the repetition frequency, that's all something that you would work out with your coating supplier and your designer prior to testing the optic. After this is done, and this is unique to laser-induced damage threshold testing, 100x magnification is performed to see if there's any visible damage. And then the number of locations that are damaged at a specific power or energy level is recorded. After this test is done, you can repeat it, and then the damage threshold is assigned to the highest power that the optic can withstand without causing damage. So that's a really quick generic description of laser-induced damage threshold. That's almost a whole sub-niche of coatings, and there are a lot of people that are very well versed in that and can walk you through precisely what thresholds they're comfortable with holding up to and what they're not. With so much exploration now done with lasers, so many procedures, like medical procedures done with lasers, laser-induced testing, laser damage testing is becoming far more commonplace than it was. But again, this is another niche of optical coatings and optical coating testing. So here are some examples of some laser damage failure. Right there, you can see a hole is burrowed by the laser, and you can kind of see a depiction of 10 different spots here. So if you're going to specify that laser damage is required, you need to know the wavelength of your laser, the energy density of your beam, the pulse length of your laser, the pulse repetition, what the diameter or the overall width of your beam is going to be, and then the intensity profile whether it's a uniform pulse or a non-uniform pulse. And again, that's all specified and should all be specified between you and your coating supplier. So one of the final tests, this is mostly for, or it is for indium tin oxide ITO coating, is sheet resistance. And this is measured with a 4-point probe. The measurement requirement that they give is ohms per square. And that's basically meaning that you have your multi-probe here, and probe 1 and probe 4, okay, are at fixed positions. Probe 2 and probe 3 actually retract or detract when they make contact with the coated surface. And as probe 2 and probe 3 touch down on the surface and complete the circuit, you get your sheet resistance requirement. Commonly, sheet resistance requirement is specified as a maximum or a minimum. And then you can get into mega ohms. Mega ohms are typically used in electrostatic discharge. Low ohm coatings, like 4 to 6 ohm per square, are used in electromagnetic and radio frequency interference filters. So what you're trying to do here is basically tell me how much pulsed electricity is going across the surface and how that's going to interact in my environment. Tolerances, if you can't specify a maximum and you can't specify a minimum, one of the things to keep in mind is a plus or minus tolerance. Maybe it has to be 50 ohms per square, but I know my system will operate if it goes up to 75, and I know it'll operate if it goes down to 25. So what we'll say on that specification is sheet resistance requirement is 50 ohms per square plus or minus 25. And that's really an easy way to specify it. There is some subjectivity on maximum and minimum requirements. If you specify a maximum, but you don't give a minimum, then you could get a very, very conductive coating and not intend to. And the inverse is true. If you specify a minimum resistance requirement, you can get a very minimally resistive coating and not intend to. So usually a plus or minus tolerance is your best practice, but maximum and minimum come into play pretty often. And if you know that you can afford lower sheet resistance than higher, specifying a maximum can make sense. And this is actually a picture of a 4-point probe here. This is very similar to the one we use internally. So that's pretty much the main part of the presentation. So now I can turn it back over to Robin with some Q&A. We probably have time for a few questions here.
Thank you very much, Dan. And attendees, if you do have questions, please enter them in the question box to the right of the screen. And we will begin here with the first question. Dan?
Sure.
How do you measure in situ optical properties and thickness while the substrate is rotating?
Okay. So this is definitely a challenge. And kind of like I talked to with the tooling challenges, measuring coatings in situ and being able to manipulate your layers to achieve proper specifications is challenging. So when you measure thickness in situ, you perform that with an optical monitoring system. Optical monitoring systems can measure the properties of an optic in real time as it's being deposited. They can measure either the reflection of or the transmission through the substrate or a witness chip. By directly monitoring the substrate or indirectly monitoring a witness chip, the coder is actually able to terminate the deposition depending on the optical thickness while they're measuring the film's refractive index and stoichiometry in real time. The technology is typically used for complex multi-layer coatings, and more often than not, we see it in the visible to shortwave IR world of about 400 nanometers, right up to about 2,000 nanometers. So that's typically how in situ, under vacuum, while the parts are spinning, we would actually measure the optical properties and thicknesses of the coating.
Okay, thank you, Dan.
Sure.
Next question here. With regards to cost versus complexity, what
Mhm.
is the impact on performance variability with higher or lesser complex coating specifications?
Sure. So yeah, this is always a sticky wicket for sure. So all optical coatings are priced by the amount of chamber space the substrate takes up, the deposition time required to complete the coating, and then ancillary concerns like washing the optic, tooling and setup difficulty, and the inspection requirements. It's pretty linear, but not always true that the more complex you make your specification, the higher the cost will be to successfully produce your coating. Some of the things you have to think about are the operating wavelength. If your operating wavelength is more than maybe 150 to 200 nanometers in the visible spectrum and maybe more than 3 microns in IR, then you're definitely going to add some cost to achieve those wider band coatings. Because you have to deposit more layers and the coatings are thicker and take longer to deposit and are harder to control, you're basically increasing your price as you increase the operating band. The same can be said for incorporating high angles of incident requirements. If your application requires like a standard viewing incidence, and your coating cost is going to be far less than a complicated off-axis coating requirement. Even if the parameters of reflectance and transmission are the same, because of the increased complexity of the coating and the requirements to meet, make that coating thicker, make the deposition time longer, and basically make the film harder to control. So angle of incidence, important, and operating band are important. Inspection-wise, the time and complexity of the specification is also going to drive your cost. If the requirement is telling you that ambient lighting and a quick visual overview in a short time period is suffice, then I would say go with that, and that's going to be your least expensive option. If you require your coating to be inspected under magnification or have a very finite scratch dig requirement of maybe say 2010, then the inspection time investment is going to be far greater, and the overall cost to produce your coating is going to be a lot higher because the inspection labor is amortized into the cost and you have more inspection labor. So that's really cost versus complexity and the impact on performance. If you need the coating to operate over a wide band and you have an off-axis requirement, definitely specify it, but understand that with these additional challenges to the coating, you're going to incur some costs.
Okay, thank you, Dan.
Sure.
Next question here. How do I specify spectral performance when I don't know how sharp the turn on or turn off regions can be?
So this is definitely tricky also. So if you're specifying your performance on a pass band or filter coating, one thing you have to consider right away is what sort of substrate you're going to be coating on. If it's a polymeric optic, it's pretty unrealistic to expect a very steep rise or a very abrupt cutoff at the end of the pass band. If your coating partner can utilize heat, if you have like a crystalline or a glass substrate, and they can utilize heat in the deposition process and control the index of their materials a little tighter, then a tighter and steeper rejection and pass band is possible. The other thing to consider here is how wide you should give your tolerance to with the pass or rejection band. If you need the rejection to start, I'm just gonna, like for example, 750 nanometers, is it acceptable if you allow rejection to start at maybe 700 nanometers? And if so, giving that additional 50 nanometers of flexibility before the pass or reject band starts, it can make your coating a lot less expensive because your coating supplier has more of a tolerance to play with, and their films can be, they can have more room for error with their film deposition. if you specify that the coating needs to be in, say, plus or minus a 5 nanometer band, then the effect will be twofold. First, you're going to have far fewer coating vendors willing to quote the program because of the difficulty, because of the complexity of the coating. And second, the cost to control the film at a tight tolerance is going to be quite significant. Not only for the coating to be applied, but also for potential yield losses here. Basically, if you have a plus or 5 nanometer band to operate in, if you come out and you're at 756 where you need to cut off and 755 is the threshold, then by letter of the law, you'd have to reject the entire lot.
Thank you. Okay, next question here. How do I specify the performance of a hydrophobic or oleophobic coating on a wide band AR coating for germanium?
Okay, so with wideband, broadband ARs in the visible and with the IR, you can actually make those coatings hydro or oleophobic with a special exit layer that bonds to a vapor deposit chemistry that's introduced into the chamber and permanently bonds to the last layer of your coating. This increases hydro and oleophobicity, so the operating band doesn't necessarily have a huge effect on how the oleo or hydrophobic coating is applied. The exception to this would be in the case of diamond-like carbon or DLC coating. DLC coatings are inherently hydrophobic films that can be used on IR materials as an anti-reflective coating, which also helps severe abrasion. The trade-off here is that DLC coatings don't perform quite as well as a wideband AR coating that utilize multiple crystalline layers. And there is some sort, there's really no hard, fast target or mil spec for hydro or oleophobicity right now. No industry's really come up with an agreed upon universal standard. One way we measure the efficiency of an oleo or hydrophobic coating is by contact angle. You can measure this with an optical comparator or a goniometer. The loose standard for this, and again, it hasn't been agreed upon, it's not really a published specification, but any coating, any hydrophobic coating with a contact angle of 95 to 110 degrees is considered hydrophobic and effective. Any coating that achieves a contact angle of greater than 115 degrees is considered super hydrophobic, which would also be oleophobic in nature. There are some laboratory claims of hydrophobic, oleophobic coatings that achieve contact angles of maybe 125 to 130 degrees, but those typically are too delicate to be mass produced. So typically, if it's a standard hydrophobic film, we look for a contact angle of 95 to 110 degrees. And then if it's a super hydrophobic or oleophobic film, we look for a contact angle of greater than 115 degrees.
Thank you, Dan. And we'll take one last question here, and here it is. How much detail do you need to put on the drawing in order to convey the design intent versus the cost?
So yeah, the design intent versus cost is sometimes hard to balance. So you can kind of see this with just a simple standard word. You can change your intent to have an off-the-shelf mil-spec AR coating versus a highly technical AR coating with a tight tolerance. Obviously, if you word it in such a way that you make it more technical or more complex, you're going to drive your cost. So for example, if you were to specify a visible broadband AR coating with less than 0.5% reflectance average from 430 to 650 at standard incidence on soda lime glass, the coating formula should be had by virtually every coating vendor. They should be able to easily achieve it, and they probably run it a few times per week, allowing for some price flexibility. If you take the exact same specification, exact same intent for the coating performance, but you say less than 0.5% maximum reflectance from 430 to 650 nanometers at standard incidence, you're making the coating infinitely more difficult. At this point, in the 220 nanometer operating band, the reflectance level, if at any point in the operating band the reflectance level exceeds 0.5%, then the coating lot must, by letter of the law, be rejected. To put that in context, a coating run can be 200 pieces of diamond turned optics with hundreds of man hours invested, expensive material, and at 649 nanometers, my reflectance level is 0.51. Technically, according to the specification, I have to reject that entire allotment just because of that 1 nanometer being 0.1% over specification. So this is really where the subjectivity of the specifications comes into play. There are really very few applications that are critical enough to require every single wavelength to be below a specific range absolutely, or a maximum. In most instances, we find this is just confusion on the proper verbiage being used when specifying the coating during the design phase. Now, in the case that the coating must maintain an absolute requirement in transmission or reflectance, then by all means you should require absolute performance, but you need to be prepared to expect higher costs, longer lead times, and potential spoilage for issues that may or may not hinder the form, fit, or function of your optics.
Thank you very much, Dan.
Sure.
And thank you attendees. We've received many good questions, and I will be sending these on to Dan later in the day. So at this time, I'm going to close the webinar. A recording of the webinar will be available very shortly, and all registrants will receive a link to the recording tomorrow in a follow-up note. And if you have any further questions, I encourage you to contact NACL. The contact information is on the screen here. I would like to thank NACL, Dan Fiore, Director of Business Development at North American Coating Laboratories, and all of you for participating in today's webinar on getting specific about coating specifications, presented by North American Coating Laboratories and hosted by Photonics Media. And NACL and Photonics Media wish you to stay well during this time. Thank you.